Hi, Algebra 2. How are you? We're going to continue on with section 4.5 today, looking at quadratic formula. And we're going to look at some situations where we have a particular type of solution known as a complex solution. And so I want to take a minute to go back and remind ourselves of the concept of complex numbers. You may remember back at the beginning of the school year, we talked about the idea of the real numbers, the set of real numbers, and kind of half jokingly said, well, what are there unreal numbers? Are there imaginary numbers? And it turns out that, yeah, there are. And so we're going to take a look at these imaginary or complex numbers, and then we'll get a chance to solve some quadratics, which have complex solutions. And so one of the things we need to remind ourselves of is what it means to be a square root. So the square root of 25 means there's some number that I could multiply by itself that gives me 25, right? And so 5 times 5 is equal to 25. And it turns out that every real number has two square roots. It has a positive root and a negative root. So we say the square root of 25 is plus or minus 5. So what happens then if I have the square root of a negative number? And what you may remember from Algebra 1 is in the set of real numbers, the square root of a negative number is not defined. Why is that? Well, because there is no number I can multiply by itself that gives me negative 25 for an answer. As you recall, if I multiply two numbers with the same sign, I'm going to get a positive product. If I multiply a number by itself, by definition, two numbers with the same sign, positive 5, or negative 5, negative 5. And you might say, well, what about negative 5 times positive 5? Doesn't that count? And no, it doesn't, because those aren't the same number. So in the set of real numbers, there's no number that I can multiply by itself that gives me negative 25 for a solution. And so somewhere along the line, somebody came up with this idea that they wanted to be able to keep doing math when they ran into this particular situation. And so they had to come up with some kind of way to work around that. And so what they came up with is this. One of the things that we remember is if I can take the radicand and break it up into a product, then each of those factors can have its own individual radical sign. So I could take negative 25 and break that up into positive 25 times negative 1. Well, why would I want to do that? Well, look right here. I can see the square root of 25 is 5. That's awesome. But this here is a problem. What do I do with that? And so somebody came up with this idea of what if we give that a name? And so they decided to refer to the square root of negative 1 as I. I is what's known as the imaginary unit. So if I take square root of 25 and I split it into 25 times square root 1, well, square root of 25 is 5, square root of negative 1 is I. So now I could say the square root of 25, negative 25 is 5i. And in particular, because I have a positive root and a negative root for 25, I have plus or minus 5i. So we've got this idea of imaginary numbers using I as the imaginary unit that stands at the square root of negative 1. Well, how does this apply when we start thinking about move this out of our way, when we start thinking about, for instance, quadratics? So let's jump over to Desmos and let's take a look at a second. So if I go ahead and I type in the function y equals x squared plus 1, here's my vertex at 0, 1. The graph opens up, right, because my a value is positive. But one of the things we notice is this graph never crosses the x-axis. And previously, we've been able to identify that the roots of the equation and the zeros of the function are represented by those points when the graph crosses the x-axis. Well, this never crosses the x-axis. When you worked on this in Algebra 1, we would say that the equation had no real solutions. But what we can do with that now is this. If I'm trying to solve x squared plus 1 equals 0, minus 1 minus 1, now I have x squared equals negative 1. Let's take the square root of both sides, and x equals plus or minus I. So I can see just in a very basic form that I can now use this idea of the imaginary unit to be able to help us solve quadratics that previously we said had no real solutions. So the imaginary unit I is defined as the square root of negative 1. And if we look at this in words, b times I, be a real number, and I is the imaginary unit. If I take that number and I square it, I get the original negative number. So in other words, if I take 5i and square it, I'm going to get negative 25. So we also have this idea of a number that's known as a complex number. So now we have a number that has a real number part and an imaginary part. A and B both real numbers, and then I represents that square root of negative 1. So every complex number has a real number part and an imaginary part. So we could have a thing that looks something like this, 3 plus 7i, or 4 minus I. And as we work our way through some of these quadratics that have complex solutions, we're going to end up having a real number part and an imaginary part. So this is the idea behind complex numbers. Let's jump on ahead and take a look at what happens when we go and try and solve some quadratics that have imaginary solutions. So thinking about this function, x squared minus x plus 2. If I was given this as a quadratic equation to solve, my a is 1, my b is negative 1, my c is 2. So let's plug this in. X equals the opposite of b, so that's positive 1 plus or minus square root of b squared minus 4 times a, which is 1, times c, which is 2, then all over 2a. So 2 times 1. Go ahead and pause the video and go ahead and simplify this down until we get your radical simplified. And I want to take a look at something that happens. So you can go ahead and check your work with me now. So negative 1 squared, that's 1, minus 4 times 1 times 2. So we said we were going to take and imagine that we're just multiplying three numbers together. Negative 4 times 1 times 2, that's negative 8. All over 2. So 1 plus or minus the square root of negative 7 over 2. So when we get to this moment, we recognize something here. We can't take the square root of negative 7 in the set of real numbers. So what do we do with that? So we recognize now that, here's my side work, square root of negative 7 is the same as saying the square root of 7 times the square root of negative 1. So now I have the square root of 7 times I, and plus or minus. So 1 plus minus square root 7i over 2 is how this equation would be solved. So now we have a quadratic with complex solutions. 1 plus or minus square root 7i over 2. And let's go ahead and take a look. Let's graph that in Desmos. So y equals x squared minus x plus 2. And we see this never crosses the x-axis. It has no real solutions. If you need just a moment to finish copying down this work, go ahead and do that. All right. So we had talked a little bit earlier about that value underneath the radical sign being negative. And you may remember this from Algebra 1. When we look at that value, b squared minus 4ac, and you can see in this example that it is printed in red. So we know that that's something they're trying to draw our attention to. And that value, b squared minus 4ac, is known as the discriminant. Okay? And according to the textbook, the discriminant is part of the quadratic formula you can use to determine the number of real roots of a quadratic equation. Well, how? So you'll probably want to take a moment to copy down this chart. The discriminant of the quadratic equation ax squared plus bx plus c equals 0, with a not equal 0, because if a is 0, you don't have a quadratic, is b squared minus 4ac. If that value is positive, so if you have a positive number underneath the radical sign, you're going to have two distinct real solutions. What about if that value under the radical is 0? Well, when that happens, the vertex is on the x-axis. Sometimes you'll hear people say that the graph bounces off the x-axis, or it touches the x-axis and turns around. So there's two solutions, but if you remember solving things like x squared plus 6x plus 9 equals 0, you had two copies of x plus 3. Well, x plus 3 equals 0, x plus 3 equals 0. Both of these solutions are negative 3. You have two solutions that are the same number. So we say one distinct real solution. And if the value under the radical sign, as we just saw, negative 7, is negative, then we're going to have two distinct non-real complex solutions. One plus square root 7i over 2, one minus square root 7i over 2. So one of the things we might be asked is to determine the number and type of solutions by examining the discriminant. So if we were given this, we're asked to determine the type and number of solutions. We need to determine what is the value of b squared minus 4ac. Well, b is negative 4, so negative 4 squared. Minus 4 times a, which is 1, times c, which is, oh, hold on, look what happened here. I need to solve this for 0 first. So plus 8 plus 8. So x squared minus 4x plus 8 equals 0. So my c value is positive 8. All right, so what happens then? I have 16. This is all still under radical. And then negative 4 times 1 times 8 is negative 32. So I have the square root of negative 16. So b squared minus 4ac is less than 0, which implies two distinct non-real complex solutions. So what have we learned today? We've reminded ourselves of the fact that there are imaginary numbers, that we use the imaginary unit, I, to represent the square root of negative 1, and that we can use that to go ahead and continue doing some math in situations that we couldn't earlier in Algebra 1. We recognize now also that we have some quadratics that have imaginary solutions. And how do we handle those when we go to solve? That we can end up having an answer that contains I, a complex number. And we've also learned about the discriminant, which is the value b squared minus 4ac, the radicand that's part of the quadratic formula. And the value of that b squared minus 4ac, the discriminant, whether it's positive, negative, or 0, tells us how many solutions and what type there are.